up to this point, we've talked about the addition principle, we've talked about the multiplication principle, we've talked about some basic counting tricks up to this point. I'm going to start talking about some combinatorial objects, specifically some classic ones for combinatorics, namely permutations and combinations. I'm going to start with permutations. There's at least a couple different breeds of these. So let's talk about permutations. So first, I got to describe to you what a permutation is. So for some set of objects or elements. So I must stress that for this definition, it's okay if you consider it a collection. All you have to do equivalently to turn it into a set is just uniquely identify each of your objects by their position, for example. And then now you have a set. It is in ordering of the objects / elements. So this would be in a row, left to right. That's at least how we're going to interpret them here. So let me give you an example. Actually, let me elaborate on this a little bit further. We're not going to be interested in just getting one permutation of a set. We're going to be interested in a listing of all of them. So these are going to be orderings. So I'm going to describe them as ordered tuples or ordered sets. So you can just imagine it as a sequence or a list, for example, of the elements. So the order here does matter. So given a finite and non-empty set A, it is a listing. It's a listing of the elements where each object in a permutation of A has a position or index. So the point is that given a finite and non-empty set A, it is a listing of the elements where each object in a permutation of A has a position or index. For example, if I give you a set A with A, B, and C, then there are 6 possible permutations. Now, I haven't told you how you know that, but I'll show you how you get it in a moment. 6 possible permutations of A. So let me list them for you. So first, let's consider the most trivial one. I'm just going to literally write out each one of the elements. I'm going to assign A to be position 1, B to be position 2, and C to be position 3. So notice I'm using rounded parentheses to indicate that there's an ordering. Another one is I could swap A and B, so I get B, A, C. Another one I could do is I could swap, let's try this one. Let's go C, A, B. So I'm just going to imagine I just shifted over C over, and then I get C back over here. So like I right shifted it like this. Naturally, I could take this and I can write it in a somewhat different way by flipping C and B. So I flip those two around, so I get C and B here, like this. Here I'm going to write B, C, and A. And naturally I'm going to have C, B, and A. I think I got them all. Got ABC, BAC, CAB. You don't see any repeats in here, right? There's no duplicates. No duplicate orderings. Here we got CAB, CBA. So notice that this one commits A into the first position. And then it just considers all possible pairings of B and C. This one commits B to the first position, and then it swaps around A and C. Then this one commits the first position to be a C. That's actually how I came up with this listing. This is a nice, easy way to try to list these. As you can imagine, I start off with the first position, I fix that, and then I enumerate from the second position to the third position, and so on. You could do something like that to list these out. The point is you have to exhaust all of them. This number could get quite big. 6 is pretty small for now. So a very natural question is the one I just alluded to. How many permutations are there of set A? Well, now let's think about this in a somewhat different way. Now, remember that it's an ordering, right? It's an ordering, right? And we talked actually about this previously when we talked about the multiplication principle. Actually, in one of our applications, we talked about when we're allowed to reuse elements. So in that case, I was able to have the first position have on, so you can think of it like I was talking about when I enumerated these. When I wrote out my list, I committed to the first position, and then I committed to the second position. Then I commit to the third position. But notice that once I commit one element to the first position, I can't use it again. That's what differs between our previous examples. So let's go back to the multiplication principle and derive a different way of going about this. So we have a process of doing this. So how many permutations are there of set A? Well, to write this down, to write down a permutation, we do the following. And let's head over here. We do the following. Well, first, we choose an element to write first. So we choose an element to write first. So there's n possible elements when I did this. Once I commit to the first position, what did I say? We can't write down that first position's assignment again. So we choose an element to write second, right? We choose an element to write second. Since I've already committed to the first position, there's n minus 1 other elements I can use. And so on. You could do this for the third, right? So choose an element to write third. So I have n minus 2 possibilities. And I can keep doing this until I've made my kth choice. Or in our case, we want to know all the possible listings of n elements. I'll come back to that thing we just said in a moment. So as I have n of them. Because I have to, remember, I want to know how to list all of the elements, all the possible orderings. Since there's n elements in the set, I'm going to do this n times. So we choose an element to write last. And in this case, we force the very last position. That's something that's rather helpful to remember, is that the last position always gets forced. So there's one possibility in this case. So what does the multiplication principle tell us then? We have an n-step process. So I do this, I do n steps. I commit to the first position, second, third, and so on. And it doesn't matter if I did this one first or that one. Notice that if I'm talking about, if I make the first choice, I lose an element, right? So when I make this commitment in step 2, every other commitment I make in the future, they don't alter in their quantities, right? They're always going to be n minus 2 many elements left, and so on. So when I make the first choice, it doesn't matter if which letter I do pick or which element I pick from A, like in our previous example. It doesn't matter which one it is, I lose one element I can use. So in step 2, I have n minus 1. It doesn't magically change to anything else. So we can use the multiplication principle. So then, by the multiplication principle, the number of permutations of A equals n times n minus 1 times n minus 2 times all the way times the 2 times 1. And we actually have a very special name for this. So we actually call this quantity that we have here, we call this n factorial, which is written as n with an exclamation mark. So just to be clear, n factorial equals the product from I is equal to 1 to n of I, where we're going to define, or it'll make sense when I explain it to you, hopefully, that 0 factorial is going to be equal to 1. So you're allowed to take on value 0 and above for an integer, and that's how we could define n factorial for counting permutations. There's a very combinatorial meaning, okay? So here's the theorem. The number of permutations of a finite set A with n greater or equal to 1 elements is n factorial. Nice, right? So, for example, I encourage you to try this for, let's try 3 factorial and see if we get 6. Well, we have 3 elements, so it's 3 factorial, which is 3 times 2 times 1. Well, 3 times 2 is 6. 6 times 1 is 6. So just as a quick example, hand calculation, that's how we got the 6 actually over here. That's how we actually got that 6. So now that brings me to talking about something strange that I brought up. I said that 0 factorial is equal to 1. And you might be like, okay, what does that mean? What's that all about? Just for context, if you're not sure what the empty set is, it is, as the name suggests, it is a set that has no elements in it. It looks like this. You don't have stuff inside of here? There's nothing in here. This is also written very often like this. So that's what I'm referring to when I talk about the empty set. So when we consider the empty set, how many ways can I list elements of the empty set? How many ways can we list the elements of the empty set? Well, think of it. There are no elements, Now, you might be very tempted to say that there are no orderings because there's no elements. But let me go back one sec. How many orderings are there of this set? How many are there? Well, remember, we are listing the elements of the set. We prescribe a number to each one, but remember, this doesn't have any elements in it. So there's really only one possible listing. There is only one listing. The empty listing. The empty listing. So, you know how we used rounded parentheses? It looks something like this. It would just have no elements in it. That's the only one that exists for the empty set. Hence, the number, I'll say hence, why the number of permutations of a set with no elements is 1, which equals 0 factorial. It's a very natural way of defining 0 factorial. It's because when I have no elements in the set, it simply means that there's only one way you can arrange the elements, namely as just an empty listing. There's only one way of listing that. So this is one reason why 0 factorial is often defined to be equal to 1. It is because of this combinatorial understanding of what that means. So you can also think about this in terms of another combinatorial object called a combination that I won't discuss yet. This is just a fun aside to talk about. So I thought it'd be a good idea I do some examples with you of applying permutations. So I thought one common way you first encounter these types of problems is through arranging words. So I want to know how many ways I can rearrange a word, for example. Maybe not in the most smartest of ways, but nonetheless ways that you may do it. So I'm going to refer to this as mochi time, because all of our little exercises here are going to involve the word mochi. So consider the word mochi, all in capital letters, like this. We're going to go through a variety of scenarios and see how we would go about counting the number of objects for each of the scenarios using what we know up to this point. So the first example we're going to go through is how many ways can the word mochi be arranged? So that also includes mochi itself. So remember that in this word here, there's something rather important I really want you to take note of, is that each of these letters in this word are actually distinct. Do you see that none of them repeat each other? So equivalent way of reformulating this is as follows. So here's an equivalent question. As the letters are all distinct. The fact that they're distinct matters here. The letters are all distinct. Well, how many permutations are there of the set where I'm going to put each one of the letters in as an element in my set. I'm going to like to think about these like a letter group, where I might group multiple letters together, but for us, we're going to keep it simple at this stage. Of the set M, with another element being an O, another element being a C, another element being an H, and another element being an I. So I have a set with 5 elements in it. I have a set with 5 elements in it. Oh, my I's a little bit off the side. Let's bring that in a little bit. H, I. My apologies. How many permutations are there of the set with these 5 elements in it? Well, it has 5 elements, and remember the reason why this is an equivalent question is because I want to know how to rearrange the letters of the word mochi. All those letters are distinct. They all are distinct elements of a set, right? There are no duplicates. So it means that when I rearrange these terms, the ordering is what I care about. The number of times I can I can arrange mochi. The same way as how many times can I assign an ordering to the elements in that set. So since there are 5 symbols, the total number of ways where the word mochi can be arranged is 5 factorial, right? Which that's 5 times 4 times 3 times 2 times 1. You might ask, Dan, how do you calculate this off the top of your head? Well, think about it. 5 times 4, that's 20, right? 3 times 2, that's 6. So I have 20 times 6. Well, 5 times 6 is 20 times 5 is 100, right? So 6 times 5 would be 120. And that's just multiplied by 1, so it's 120. So it's 120. That's pretty cute, right? Let's do another example. Now, do you take note of how I organized my thoughts here? Now, you can think about this in several different ways, but this is one common way. Is you try to think about, okay, all these letters are distinct. I have to assign an ordering to them. I have 5 of these. Now, I want you to think about like letter groups for this next example. Example. How many ways? So we're going to just think about, if we have the word mochi, how many ways if M and O must be together. So I want to know how many ways you can arrange the word mochi if M-O, these 2 letters must be together in the string. Well, let's just apply the exact same principles. All my elements are distinct, right? M-O is distinct from C, is distinct from H, distinct from I, right? But here's the thing, I want M and O to be together. What can I do? What can I do? It's really nice and easy. You just apply the same principle we did right here, right? Same exact principle. We use the same principle. Notice that I put each letter as a letter group, in the set. How many did I have there? I had 5. Well, I can do the same thing here. So you treat the elements as letter groups, i.e. you have MO as one element. You have another letter group that's a C, another letter group that's an H, and another letter group that is an I. So you can use the exact same setup now. So how many elements are in this set? There's not 5 anymore, now there's 4. There's 4 elements in the set. So now we just ask the same question. So as there are 4, I got 1, 2, 3, 4, right? I have 4 letter groups in the set. The number of ways of arranging the word mochi, where I'm in a word together, is 4 factorial, right? There's 4 elements in that set. It's 4 times 3 times 2 times 1. Okay. So we got 4 times 3 is 12. 4 times 3 is 12. Times 2 is 24. Times 1, still 24. So that's our second example. I'll just call this 2. Let's get another one in here. Let's do one where we have to actually, we have to fix a position for something in the string. So here's our third example. How many ways can we arrange the word mochi where every arrangement starts with M and ends with what? Let's make it end with I. So now we're considering the scenario where I want to know all possible ways that you can arrange the word mochi, but M has to be the first letter, I has to be the last letter. So let's pick up the same principles that we did over here and think about it. Our arrangements will look something like this. It always will have this form where I commit one to go here, another one to go here, and another one to go here. What are those other ones? What are going in here? What are going in these spots? Most certainly not M or I, right? What can go in these spots without repeating themselves? Well, O, C, and H, right? Do you see very quickly how we're going to answer this? So really, what matters when we're trying to find all the permutations is that, really, right? It's the number of permutations of this set. Because once you've determined one permutation of this set, you just tack on M and I at the start and end respectively, correct? So we have 3 letter groups. O, C, and H. Hence, the number of ways to arrange mochi as described is 3 factorial, right? Because it's a set with 3 elements in it, which is 3 times 2 times 1, which equals 6. Now you might ask, Dan, how do you know, did you double check that? Do I need to make sure? Well, if you're not sure about it, I encourage you to enumerate them all or just generate all of them. So for example, there should be 6 of them. So most certainly I should be able to do this. Well, let's try to put them all through. So much. I'm just going to fill the blanks now. Got Mochi, right? I can always flip this in reverse. I got H, C, O. I'm going to now swap C and O. So I got C, O, H. I'm going to flip and reverse that, so I get H, O, C. And then I'm going to do the similar thing that I did actually in my first example with permutation. This actually should remind you of the very first example we did of me showing you the list of all the permutations. So my listings. So these are all 6 possibilities, just like we talked about before. So this is just to confirm the count that we got. So there's 6 listings here, 6 permutations, and we're done. So that's all I have to really say about permutations. But now we're going to go back and revisit how we derived the number of permutations of a set. Now, previously we talked about this idea of having it where we pick the elements, but we can reuse them. What if I was not able to reuse them when I pick k objects from a set of n objects? This brings me to the concept of a k-permutation. So let's talk about a k-permutation. So now we're going to talk about k-permutation. So let me define what that is. I don't need to be as sophisticated about this. So suppose we wish to consider some ordering of k elements without repeats. So you're not allowed to reuse the elements. We've previously seen what we could do with repeats when we talked about the multiplication principle. So from a set of n elements, such an arrangement is called a k-permutation. Specifically, it's a k-permutation of that set. So just to give you an example of what I'm talking about here, let me just get a different marker. Okay, we'll go with this one. So suppose that I choose no. Let's do the example here. So for example, if A is going to be the set A, B, and C, so I have 3 elements in here, namely A, B, and C. I deliberately chose this example so that way you can compare it against some of the other definitions that we had. It has n is equal to 3 elements, right? And for each 0 is less than or equal to k is less than or equal to n, we can list them. So I'm going to go through each value possible of k and see what we get, okay? Just going to flick this marker off. It's gone. It's gone. That was quite dramatic. So if I consider k is equal to 0, well, how many orderings are there when if I pick no elements? Well, there's just one that exists, right? The empty listing. So it's only the empty listing because I didn't pick any. If I pick k as 1, there are 3, right? Namely, you got A, B, C, each in their own listing, just by themselves like that. How about k is equal to 2? So there are 6 in this case. We're going to have AB, we're going to have BA, we're going to have CA, then we're going to have, we'll have AC, then we'll have BC, then we'll have CB. So notice that it is just simply, I want if I pick 2 of the elements, I want to know all the possible ways I can order them. So in this case, you can imagine I pick the first one, and then I pick a second one, right? It should ring a bell with something we talked about when we derived the number of permutations. It's a very similar process. It's just that we're not going to go all the way and select all n. So you could do this again. Now let's suppose that we consider the case when we have 3, which happens to be n in this case. So again, there are 6. We have A, B, and C. We have B, A, C. We have C, A, B. We have C, we have C, A, B. We have A, B, C. We have, C, A, B. Whichever ones do we got? We got A, C, B. I'll tell you up front that this is actually a fairly easy example. We have C, B, A. Why do I say that? I said this actually previously, or at least a little earlier, is that once you consider the last position, what did I say previously? It forces the last position. So do you notice right away that all I did was just tack on the last element on each one of these? So for example, when I want to get the last position, like we did when we computed n factorial, when I chose n elements, this is when we get k as n. So it means that we only have one choice at the end. So we immediately know what the final position is going to occupy for what element that is, right? We know what the last element's always going to be. That's why this should be no coincidence that these are the exact same numbers. So, anyways, let's talk about how we derive the number of k permutations of a set with n elements. So hopefully the definition is clear to everybody. So, remember, the big idea here is I imagine I'm going through and fixing a position for each one of the elements that go in the ordering. I give each one a position, but I'm only allowed to pick k of them. So let's go back to what we did before. Like before, for permutations, for perms, we can derive using the multiplication principle, the number of k-permutations of a set of n elements. As we simply pick k of the n objects, right? So you can almost look at this like a special version of what we just argued before when we came up with the number of permutations of a set A. So what you did was we select a first element, right? That's what we did last time, which had n choices or n possibilities. Then we pick a second one, right? We're just setting it up like a series of choices. We're committing to each one of the positions. Like the second element, how many can I do? N minus 1, there's n minus 1 choices this time. And we can keep doing this until we've selected k many, right? So select the kth element. Now, you have to be a bit careful about this. Okay, so it's going to be that there's n. So how do I get to pick in total if I were trying to enumerate all of the permutations of a set? I get n of them, right? But I'm picking k. But remember, k could potentially be 0, right? So imagine if I picked none, right? Well, it has to still be true, right? It still has to be that it gives me the correct count like we had over here. Well, we have n minus k minus 1 many possible choices, which is n minus k plus 1 choices. If you're wondering why it's k minus 1, it's because remember that when we start our counting, we're starting at 1 in this list, so it's somewhat deceptive. So keep that in mind. So just as a quick example of what I mean by this, you can imagine, because remember, we're also starting from the back end, right? So you can imagine if I were to pick, say if I only picked one element, then k would be 1, so it's 1 minus 1, which is 0. Then I would have n choices, just like I have here. If I have 2, then I would have how many? I would have n minus 1 choices, right? So please don't let this k minus 1 throw you off. That's because of the way we're indexing when we make the choices. Because we're starting, when I write this out like this, we're actually starting from the bottom and we're subtracting up the correct number of elements to the appropriate spot in our list. Because you got to remember, we count downwards the higher the number gets. So you can imagine this in the case for which you select n elements. This would be n minus 1. So this would just end up being one choice, right? Because we left with one choice. We notice that's why. So hopefully that is clear where this k minus 1 comes from. It's just the way we listed them. It's about the way we list them. I just need to make sure that we're keeping the appropriate count of choices. So now we can use the multiplication principle. So by the multiplication principle, this number is as follows. It's n times n minus 1 times n minus 2 times all the way to n minus k plus 1, which this is equal to n factorial over n minus k factorial. Now you might ask, where did this come from? Well, remember, when you write this out, you have all of these terms. Notice that if I divide, so if I write that out, I divide by n minus k factorial, I take out all of the useless terms, the ones that we never end up using from n factorial, and we get that. This is just one way of writing this down. Very often, this right here gets written in a specific way. So this is often written as, so this is denoted as PNK. So this is the number of k permutations of n objects. So P and K there, that equals n factorial over n minus k factorial, or equivalently this. Pretty nice, right? So let's do a couple of examples of applying this, just to see what we can use this potentially for. And keep in mind, it doesn't have to be about using things. I find a very common mistake people make is that they get obsessed with that it has to be used. It can't just be studied on its own regard. It's a feature that we can use it for things. Okay, let's do a couple of examples. So how many ways can 3 of the letters of the word cake, or cakes, let's go cakes, of the word cakes, be selected and written in a row? So how many ways can 3 of the letters of the word cakes, which I might note has 5 letters, be selected and written in a row? Well, take note, akin to some of the previous examples we did, all the letters in this are distinct. So we have 5 distinct letters. We have 5 distinct letters. Each can be considered its own letter group, as we discussed previously. Letter group. So that means that we end up with a set that looks like this. So you can imagine it just like we were given a set like this. And we select 3 of them. Well, what is that? What is that, everybody? What is this? It's just determining the number of 3 permutations of this set. This is just the 3 permutations of this set. And in total, the number of these are as follows. Okay, I have 5 elements. I choose 3 of them, right? So what is that? So there's a feature of this notation that's rather helpful when you talk about P and K. Remember, N is the number of elements, K is the number of elements you get to pick from. So I get to pick 3 of them. So very naturally, I have P 5, 3. So that's 5 factorial over 5 minus 3 factorial, which this is 5 times 4 times 3 times 2 factorial. Usually the trick is you write it out until one of the largest factorials of the denominator appears. Then you can cancel them over 2 factorial, because 5 minus 3 is 2. So I have 2 factorial, this 2 factorial, and that 2 factorial go say bye-bye to each other. So I end up with 5 times 4 times 3, which equals 60. Because 5 times 4 is 20, multiplied by 3, that's 60. So now I want to do something similar to the above scenario. So hopefully that is clear, everybody, where I got 60 from. I want to do a very similar scenario. Now, let's think about this. So consider the same scenario above, but the last letter must be K, the capital K. It has to be K this time for the last letter. This should remind you of one of the previous examples we did, except we have to be careful here, right? So remember that I want to know how many ways you can have 3 of the letters written up, selected and written in a row, but the last position now is going to be fixed as a K. So what can go, so notice I have 2 other spots available, so I'm actually choosing 2 letters to go in this sequence. Which letters though? Because K is already being used, right? So I'm choosing from this set. I get to pick C, A, E, or S, akin to our previous example here. Notice K isn't there. We have C, A, E, and S. Let me just write that A a little bit more carefully. But what is this? So this is for the remaining positions. But what is that? What I'm asking is actually an equivalent question, akin to our example previously where we talked about mochi with the first letter and last letter being fixed. I just need to know the number of 2 permutations of that set, the one without the K in it. But what kind of permutations? I need 2 permutations of that set, correct? I'm pretty sure that's what I just said, but I just want to make sure it's clear. So let's clarify this. So this is just the number of ways is the number of 2 permutations of this set, CAES, which how many elements does CAES have? It has 4 elements in it. It has 4. So this is going to end up being P42, which equals 4 factorial over 4 minus 2 factorial, which equals 4 times 3 times 2 factorial. Then I end up with my then I have another 2 factorial. These 2 are going to cancel. So I end up with 4 times 3, which is equal to 12. Piece of cake, right? That's all I have to say about permutations, at least at this stage.